Alright, hello. Today I will be covering my top 10 algorithms candidate for the class CIS4390. My name is Hong Yoo, and the algorithm that I've chosen is the AVL tree. So here is a quick overview of what the presentation will consist of. I have a few pictures and my paper presentation that I have on my computer that we'll follow along with. And so let's go ahead and go over to our paper, and the first topic is the introduction. And the AVL tree that I've chosen as my top 10 algorithms candidate stands for Edelson-Velsky and Landis tree, and it's the first self-balancing binary search tree of its kind. And the way that the AVL trees work, whenever you insert or delete nodes, it pretty much balances the tree so that in any node, the AVL tree, at any node, the two subtrees never differ more than 1 in its height. So further along, we're going to just go over some background information. And the algorithm description is a binary search tree that it's a more robust binary search tree because of the fact that whenever you insert or delete, it rotates the nodes so that the height of any two subtrees are never differ by more than 1. So let me show you an example of what that looks like. So here is an example of an AVL tree. If you look, classic scenario of the binary search tree where the smaller numbers go on the left, larger numbers on the right. However, if you look on the left side of this 50, the height of that subtree is 1, 2, 3, which doesn't differ more than 1 by the height of its other subtree, which has a height of 1, 2, and 3. So if you also look in any of its other nodes, you'll notice that it's the same also. Because if you look at the 72, the two children consist of a height of 1 and 2 and 1 for the other subtree. So 2 and 1, the difference is only 1. Alright, so what is not an AVL tree? I drew this little diagram for you guys. So if you look, we're actually looking at the root node, and the height of the subtrees on the left here consists of a height of 3 and 2 on the right subtree. However, on the other side, we see what is not an AVL tree, because on the left subtree here, even though everything within the left subtree is it doesn't seem like it's too far off, but if you look, the height of the left subtree is 4, while the height of the right subtree is only 2, which differs more than 1. So that's an example of what is not an AVL tree. This would be your average binary search tree. Alright, so the assumptions that I've made, I've stated them earlier, but to put them formally, it's 1, that every node subtree must differ in height by at most 1. And the second condition is that every subtree within an AVL tree is also an AVL tree. So that pretty much means that starting from the root, your AVL tree will never, your subtrees will never differ by more than 1, and within every single node inside of that, the condition still holds. So intuitively, it's recursive and it allows for more complex features that way. Alright, so I've shown you that first diagram, and let's go ahead and see how these rotates work. Let me pull up another diagram. There's actually 4 cases, well 5, the 5th one being balanced, where when you insert a node, you can either have a balanced tree where all the heights never differ by more than 1, or it's unbalanced. And when you do have an imbalance in the subtree, then you find where that imbalance is, and you have one of these 4 cases: the left-right case, the left-left case, right-right case, or the right-left case. And this is pretty much the rotations that you have to do. So what ends up happening is you actually only need 2 main algorithms for this, and all it is a left rotate and a right rotate. And once you define those 2 rotates, you can pretty much reuse them. So if you, for instance, let's say we need a left-right rotation, then all you do is you go down to the bottom and you do a left rotate, and then you go up to the next parent and then you do a right rotate, and that should set your tree so that it's balanced. Alright, so let's go ahead and look at the code for that right here. The pseudocode for it, it's pretty simple, and that's part of the reason why I chose the algorithm. The left rotate will follow along, takes in a node. Node A will be the root, and then node B we set as the right child. And then the next thing we do is move some pointers around. The root's right child becomes the child's left child, and then the child's left child becomes A. So a visual representation of that would be something like this. From this side to that side is a left rotate. This yellow box would be A, and yellow box is A. A's right child would be assigned as B, and then we assign the 2 pointers. This would be pointing to that, and then A's right child would be reassigned to beta, and B's left child would be assigned to A. So there we have the left rotate, and all it is just 3 pointer changes. And then the other way around is the right rotate. It's the same thing, just with different sides. The same old 3 pointer changes. So as you can see, the code is really simple, and once you write the left rotate and right rotate, all you need to do is figure out the logic to figure out if you need the left right case or the right left case. But that's all logistics. It's pretty simple to do. So continuing on, conclusions as far as the AVL tree design. Because of the way it's designed, whenever it inserts or deletes, it has a height check, and if it's unbalanced, it makes the rotations that it needs. So whenever you have to search, insert, or delete, the tree is already balanced. Alright, so let's go look at some of the runtime and run space. In the worst case, the space complexity that you need for an AVL tree is just an upper bound of n, because you only need to store the nodes, which include the pointers. And because it's a tree, that's pretty much all you need. And all you do when you rotate is just reassign pointers. So there's no extra space needed. Now for time complexity, as far as search goes, because of the way AVL is designed, your height will always be bounded by the log of n, and because of that, the AVL's search traversal will never be more than log of n. So thus it's bounded by an upper bound of log of n. Same thing with insert. The log of n comes from the search, or I guess better phrase, the traversal of the tree, because if the furthest down you traverse is bounded by log of n, and the actual insert is is pretty constant time because all you do is create the node and you assign a pointer to it. So that actually is consumed by the upper bound of log of n, and similarly delete is the same way also. The upper bound of log of n is bound because of the traversal, and then the deletion and the rotations is also consumed by the upper bound of log of n. Alright, so there are actually some variations and spin-offs to the AVL tree, and I've actually pointed out two. And one of them is the binary search tree, which is pretty much your standard tree. It's pretty much your classic tree structure. However, it doesn't balance itself. So the biggest thing to note between binary search trees and AVL trees is the fact that binary search trees aren't balanced. So if you input a starting root of, let's say, 100, and all the numbers after that happen to be decreasing, so let's say you have 100, and then the next node you get is a 95, and the next node you get is a 50, and so on and so forth, the tree will become very unbalanced toward one side. So that can pretty much lead you to a search complexity of n squared, I believe. But either way, that's the biggest point that I want to mention, is just the fact that AVL trees, it doesn't cost much to set it up and set up the rotates, but it'll help a lot in the long run because of the upper bound of log of n. Alright, so the other variation of the tree structure is red-black trees. And red-black trees are actually a little more efficient than AVL trees are, but they're marginally more efficient. So both of those structures have a search, delete, and insert time complexity of log of n, but because of the way that red-black trees are designed, they're a little bit better balanced than AVL trees are. Let me show you a picture of what that looks like. Pictures. Alright, so here's a red-black tree. Some of the conditions that the red-black tree has is that each node is colored either black or red. It can be represented by one bit, one being red or black, depending on how you implement it. And the root is always black. However, at each level, you pretty much change colors. So whenever you have a black node, the child of that black node, if it's not null, is going to be a red node. And a red node is followed by two black children. So that's the way that that's designed, and all these null pointers on the bottom can actually point to the same null pointer, and so on and so forth. However, the thing with that is it's marginally faster than AVL trees, but AVL trees seem to be more popular. They usually tend to be more popular because it's simpler, and not only that, it's pretty much that. It's simpler, and it's easier to teach and easier to implement. So finally, the reason why I chose AVL trees is because it's fast and efficient, but it's also very simple to implement. And personally, one of the main reasons why I did choose this is because AVL trees were actually the gateway to algorithms for me, because it's very simple, but it does a complex algorithm at the same time, and it actually has just a little bit of edge of challenge in it, especially delete. AVL's deleting function is a little more complicated, but that's what you want to look for when you look into academia. So because of the fact that AVL trees are ever so complex but simple to implement is the reason why I chose it as my top 10 candidate. It does a lot, but it's also very welcoming to people who might be wanting to learn algorithms without having to know a lot of background knowledge. Also, it's just a bit more intuitive than red-black trees are. So that's why I chose AVLs over that. So closing thoughts, AVL trees are fun and efficient. They get a lot of stuff done, and tree structures are very popular because working with pointers is simple and the time and space complexity is minimal. Well, I wouldn't say minimal, but the space complexity is very small with pointers. So because of the fact that it can help people learn algorithms better or encourage them to learn algorithms, I actually promote this as my top 10 algorithm, because the more people we can get to learn algorithms, the better algorithms we can get. So that is why I've chosen AVL trees as my top 10 candidate, and that is my presentation. Thank you.